Dear friends, today we'll be starting with a new topic called as processor organization and architecture. Now, first let us understand what is processor organization. Now, we would be aware that there are different types of families of processor: 8089, 8086, 8085. So, how are these processors interconnected with each other? What are the different forms of memories that are being used when we are working with this processor? What are the different forms of laws that are associated with these processors? That we'll be looking at into this entire topic along with the architecture of 8085 and few examples of 8086 processor. So let us go ahead and start with the first topic. Now, classification of processors. Now, why classification of processor is important? Because processors are being classified into two categories. One is it depends on the different type of memory organization what these processors are using. At the same time, it also depends upon the different type of instructions what they are using, whether it is RISC or CISC, which we will be going at and looking on it one by one. So, as we have seen that category of memory organization that defines the processor, there are mainly two types of category what processors are using. One is called as von Neumann architecture, and the other one is called as Harvard architecture. These two architectures we will be seeing in the upcoming topics of this chapter, where they have been defined in brief. Secondly, what are the different type of instructions what they are using? Is it RISC or CISC? So these are two types of instruction types what the processors are using. Now, what do you understand by RISC and CISC, and how are they defined and why are they important? So when you look at RISC, first of all, it is called as reduced instruction set computer. Reduced instruction set computer, and the IBM 360 system created in 1964 was probably the first modern processor system. Now, when you look at this, this was been developed by IBM. Now, what was the advantage of creating RISC? That is reduced instruction set computer, and CISC is called as complex instruction set computer. So one is called as reduced, one is called as complex. Now, first thing, what were the advantages? Micro-coded control, like the control was very fast. It was micro-coded. Your coding, what you did was onto a chip. So computing became fast. It was able to reduce the semantic gap. The semantic gap means the gap that was existing between the input and the output. So it was able to reduce it. It was able to execute faster. It was able to produce hardware flexibility, like you can expand and you can contract the hardware as per your requirement. And it was able to execute fewer instructions. Those would have a better performance. Here, it was able to utilize the cache memory, because cache memory, you are aware that such sort of memories are used for the fast performance and they require less space. And these memories also store the instructions what you are frequently using when you're typing in it into your computer. instructions with different sizes and execution cycles, which make CISC instructions harder to pipeline. Now, when we moved into the middle of 70s, people began to doubt the design philosophy with CISC because CISC was a little harder to code. And when it was difficult for them for using the pipeline instruction, like pipeline means the output of one instruction will be the input of the second instruction and so on. So it had a very complex instruction set. Decoding was taking very large time, and execution of such instructions were complicated, and they were also considered as the time consuming. Overhead bought by them slowed down the execution of those more frequently used simple instruction. So more and more overheads were created and more simple instructions were becoming harder to execute. And this indirectly reduced the performance of the system, and it was affecting the performance of the computing system. So with this complexity, RISC was being designed so that RISC chip should have the following set of instructions. It should have few instructions. Fixed size instructions in a fixed format. The instruction format should be fixed. Execution on a single cycle of a processor. The executing cycle should be on a processor and it should be faster. And it should have load and store architecture. You define the predefined instructions that need to be performed, and then those instructions should give you the desired output. And that is called as your load and store architecture. And it is controlled by a hardwire control. And superscalar and speculation is possible. Like it is able to scale. Scale means either you can increase the size or at the same time you can decrease the size also. They realized that RISC promised higher performance, less cost, and it was easy to be designed because the algorithm used while preparing RISC was very simple as compared to CISC. Now let us have a comparison between CISC and RISC. CISC is richer instruction set, some simple, some very complex, as the name suggests, complex instruction set computing. It requires to take more than one clock to execute one instruction. So imagine the time it would take to execute if you have a pipeline of instructions. Instructions of a variable size. Instructions interface with complex memories in multiple mechanisms with complex addressing modes. So when you have the complex addressing mode, the retrieving of those instructions also becomes very complex. And here, there was no pipelining that was being used. You execute one instruction, you get the output, then you go and execute the second instruction. Simultaneously execution was not allowed. It had only upward compatibility with the processor family. And it was coded on microcode. When it was being coded on microcode, the control established was called as microcode control. And it worked well with simple compiler. If your compiler, which compiles with decodes and encodes the instruction, is complex, CISC will fail. Now let us go ahead and look at RISC. It is simple, primitive instructions, and the different addressing modes were being used. The instruction set executed in one clock cycle. So when you look at CISC, it required more than one clock cycle. Now the time has reduced to one clock cycle. It was uniform length instruction and a fixed instruction format. So the instruction format was being predefined. When you had the instruction format as a variable instruction, it can be 2-bit, 4-bit, 8-bit. Here the instruction format was being predefined. Instruction interface with memory with fixed mechanism. Here pipelining was used because of the fixed instruction format, and secondly, the time was been reduced to one clock cycle. Instruction set is orthogonal, like overlapping of instructions functionality. And again, it was being hardwired controlled, and it also played an important role when it started working with the complex compiler. Like CISC was not able to work with the complex compiler. Here, RISC was able to work with the complex compiler also. Now, after this was developed, RISC and CISC, the different versions came into picture. One was called as Advanced CISC and Advanced RISC. What were the features of Advanced CISC? Segmented memory model. It had only a few registers involved. Crappy floating point performance. Again, the performance was into a floating point type system. And the length of the registers were reduced, and it had only few registers that were considered. In case of advanced RISC, superscalar and out of order execution, it had a large number of registers that were being used, and it was a fast floating point performance. Now, let us have the summary of the architecture which was being prepared between the MIPS R2000 RISC and Intel 8386 CISC. Now, when these components were being announced, date of the announcement was 1986 and 1985 in case of CISC. The instruction bit that was used in RISC was 32-bit. Here, in case of CISC, was variable. Address space in case of RISC was 32-bit. Here, in case of CISC, 8386 was 32-bit, segmented with paging support. So paging support means it required more amount of memory. Data alignment was being allowed, like you can compress or change the size of data, and the data can get aligned according to your storage capacity, which was not allowed in case of CISC. The addressing mode, data addressing mode was 2 as compared to CISC, which was 11. Protection that was used in case of RISC was page. Here it was segmented schemes that are being used. Integer registers, 31 GPR into 32 bits. In case of CISC, it had 8 GPR into 32 bits, 6-bit segment registers into 16 bits, 2 other into 16 bits. And here it required a floating point format, 754 signal, and it required, in case of CISC, it required 754 signal level, and it can be extended. Now, this is architecture with regards to RISC. MIPS R2000 RISC. This is a small example. Let us look at it. First, it will fetch the instruction. Then it will decode the instruction. After decoding, it will execute. Then after executing, it will store the instruction into the memory, and then write back. So what do you understand by instruction fetch? When a programmer writes an instruction, it will fetch the instruction. Then it will decode those instructions. Decoding means it will break the instructions into the different format and it will form a decoded register for those instructions, and the instructions will get stored over there. After decoding, it will execute the instructions. Now remember, when you're decoding the instruction gets converted into the machine language, and then the memory is being allocated, and then again you return back and you write the instructions. Now when you look at the architectural diagram, your computer is being connected to a memory, it has been connected to the different register files, it has been connected to the different auxiliary memory, ALU, and multiplexer, so that more than one instructions can be executed. Here in this diagram, you will see next SEQ. Next SEQ means a sequence, and you have a adder which is directly linked. IR means instruction register, and IMM means immediate. So all of these systems are being interconnected with each other. For example, when the instruction is being given to a PC, it will directly go to the memory. From memory, it passes to the instruction register, and simultaneously the instruction goes to the adder. The adder and memory are being linked with the instruction decode, that is called as your ID. From ID, it is directly linked to the register files. The register files will store the instructions, and then it goes from the RS1 to the register files. Then it goes to the instruction decoder. From there, it goes to the different multiplexers which are directly connected to the ALU. If it is 0, if the value is 0, then it goes back, then the branch is being taken back with the help of the multiplexer. Else it gets executed to the memory, and with the help of multiplexer, you can directly store the instruction, or the instruction returns back to the PC, which we call as your write back. Now this is the architecture of Intel 8036 CISC. Here again you have the different status flag. When you say status flag, it is the address flag, data flag, and the control flag. Now you have a 3 input adder, you have the descriptor registers, you have limit and attribute PLA, you have the different ALUs that are being connected. It may be ALU which has been executed, ALU which needs to be executed, and it may be having a ALU controller. And then you'll be having the protection test unit. So decoding the sequence, and then you have the control room. All of these things are being interconnected. You have a request prioritizer. It will hold the request, it will execute the request, it will give the error if there is some error into the request, and then this button is also responsible because it will give the error and it is also required to reset. So this is being it is being converted with the help, the request that you give is being controlled with the help of the different address drivers, pipeline, bus control system, and multiplexer. All of these are being connected to the adder. You have a page cache. Page cache means it will store those amount of pages which are being temporarily used or at frequently that are being used into the system, so that when the instruction comes in, the data can be retrieved from the cache at a very, very fast interval. And simultaneously, it also has the control and attribute PLA. So attribute means the properties. The properties of the PLA are also being stored over here. Now this adder is being connected into a bidirectional with the help of the address bus to a 3-bit adder, which is directly linked with the descriptor registers. These are the registers that describes the location, like the start point and the end point of the registers, like the location where these registers are stored, the memory location, the index, and then they have limit and attribute of the PLA. These have been directly connected with the effective address buses, which may add, multiply, register file, and this is being controlled with the help of the control buses that are directly being connected to the decoding and sequencing. For controlling this overall operation, you have a dedicated ALU buses. ALU buses are the arithmetic logic unit buses, which are directly connected to the register files and multiplexer and trans receivers.